Hi, welcome to Mathematics for Machine Learning. So in calculus, we've already introduced the gradient as a generalization of the derivative for multivariate functions, or functions that take multiple input parameters in order to compute an output value. And in this case, the derivative was not just a single number, but you had this vector of partial derivatives that had as many dimensions as number parameters of the function. Today we'll learn about the generalization of the second derivative, the so-called Hessian matrix, and we'll learn how to use the gradient and the Hessian matrix to do approximations to multi-parameter functions. And well, let's get into the multivariate Taylor expansion. So we're starting out by saying that we have a multivariate function where y is the function of not just a single parameter x, but n of these x n. Then we said that for any xi, we can build the partial derivative. And the partial derivative we got by looking at the difference between f at our current parameter vector x. So we remember that we have all those n different parameter values. But what we're interested in is the partial derivative of our function, which is y, so the output of the function with respect to our xi. In order to get the partial derivative, well, we still keep all our other dimensions in there. So we still have our x1 through xn, but our xi we actually now vary slightly. So we look at the difference between f evaluated at all the x's as before, where just the ith coordinate is changed by a small difference h, and f at our original value x, where xi is unchanged. And this difference we then divide by the magnitude of this deviation h, and the partial derivative is then defined of the limit of this difference divided by h, where h goes to 0. And the gradient was the vector of all these n partial derivatives, so it's a vector of size n. So here we see that for this multivariate function, which goes from Rn, so it takes a parameter input vector x that is n-dimensional and computes a single output value. Then the gradient vector of this function f of x with respect to the vector x is the vector of all the partial derivatives. So we're taking the partial derivative with respect to the first coordinate, the second coordinate, and so on, up to the nth coordinate. And the gradient is typically denoted by this triangle, or upside down triangle, which is called nabla. So it's the gradient of f with respect to x. Or this capital D, where D stands for derivative. And when it's always clear with respect to what we want to take the gradient, so if f is a function, for example, of x, and we just want to take the gradient of f with respect to all the complete x, then we can also write simply the gradient of f of x. Whenever we assume that the x is clear, then we would write it without the underscore x. Using the gradient, we can build a linear approximation to the function. It's a locally linear approximation. What does that mean? Well, we have the gradient f of a function f, and we pick a point x0. So here in this picture we see our function f. That's the black function here. And at this point x0, so here we have x0, we want to build a locally linear approximation. And what do we want? Well, we want an approximation that at this point here has the same function value and also the same gradient, or in this simple one-dimensional visual case, the same derivative. And how do we get that? Well, in order to get the same point, so we can just say that at this point x0, the function should be f of x0, right? So here we have f of x0. And now we have to think about what happens if we change the input to this function. So if we go away from x0, and that we take into account by adding this term, which is linear in the gradient. So it's the gradient at this point x0 of the difference where we actually want to evaluate the point. So that's x, and this point x0. So this here basically you can think of as a difference in x. You can call it delta x equals x minus x0, and then you basically multiply this difference vector, which is 0 at the point x0, and then actually so making this whole term equals to 0 here. And non-zero is if you go away from x0. And how do you go away? Well, you go away along the gradient. So you're adding a linear term in the gradient. And as a result of that, if you would actually take the gradient of the resulting function, you would again get the gradient of f at this point x0 back. So in the multivariate case, we are approximating f at the vector x as f at the vector x0. So remember, x is any point on from the domain of f, and x0 is this one specific point where we want to do this locally linear approximation. And we're adding to this f of x0 a term that is 0 at x0, namely the difference between x and x0. So if we plug in x0, this term becomes 0, so we're just getting f of x0 back, times, well, the gradient of x at f0. This locally linear approximation can be generalized to an arbitrary polynomial. So let's look at single variable functions first. So for a single variate function, so those are functions that go from R, so one-dimensional R, to R, so from the real line to the real line. Then the Taylor polynomial of degree n of f at this point x0 is defined as Tn. So that's how we denote it. We call this Taylor polynomial Tn. And it's defined as the sum that goes from k equals 0 to n of the kth derivative of f at x0 divided by the factorial of k times the difference between the x where we actually want to evaluate the function and our point x0 to the power of k. So if we start out with k equals 0 to n equals 0, then we would have a constant. So the blue line here. If we go to n of 1, so the polynomial of degree 1, we would have our linear approximation. So it's a function that at the point x0 here has the same function value and the same derivative, and then goes linearly. If we increase n, so the order of the polynomial, we get a higher order polynomial. And it turns out that this polynomial and the function will here at this point x0 have the same derivatives up to the degree of the polynomial. So what does that mean for the t of 0, so the polynomial of degree 0? Well, in this case, the 0th derivative just means it's the function value itself. So the only thing that needs to match here is the function value. For t1, so for a polynomial of degree 1, the function value here need to match and the first derivative need to match. Here at t5, the function value needs to match and the first derivative, the second derivative, the fourth derivative, and the fifth derivative, and so on. And what you see is, if you increase the polynomial even further, we more and more approximate the function. So the higher the polynomial, the more accurate this approximation is becoming. But you also see, if you go further away, then this approximation doesn't look very good anymore. For example, here for a polynomial of degree 5, you see that this polynomial goes away from the true function value quite rapidly. So here you see the difference, and you see how the difference increases a lot. However, as long as you're close to the function value, a high polynomial will give you a very good approximation. And finally, if we allow n to go to infinity, then we get the complete Taylor series. So the Taylor series for a smooth function f that is infinitely differentiable is just a Taylor polynomial where n is allowed to go to infinity. So it's t infinity. So it goes from k equals 0 to infinity of the same term as before. So the kth derivative at this point x0 divided by k factorial times x minus x0. So x0 is the point where we do the approximation to the power of k. And if the Taylor series is exact in the sense that f of x is the same as the Taylor series, then the function is called analytic. So we have seen that using derivatives and by taking higher and higher order derivatives of functions, we can build polynomials that better and better approximate functions. So far we have done this only for univariate functions where we can take these higher order derivatives. How about multivariate functions, or functions that have multiple inputs? Well, we've already gotten to know the gradient vector, so the vector of all the partial derivatives, as a generalization of the first derivative in the case of multivariate functions. How about higher order derivatives? For the second derivative, or the generalization of the second derivative, is called the Hessian matrix. So for a multivariate function, so the function that takes a d-dimensional input and outputs a single real number, the Hessian matrix is the following d by d matrix. It's the matrix of all the second order partial derivatives. It's denoted by d square of x of f or nabla square of f. Now, what are these second order partial derivatives? Well, on the diagonal, this will be the second derivatives, or if you think about this function that keeps all the parameter values the same but only changes a single one, the function that we built in order to build the partial derivatives. If you take the second derivative of that, you would get the diagonal values. And on the off diagonals, we actually have the partials with respect to one dimension and then with respect to second dimension. Now, what does this mean? Well, it means we're starting out by the gradient and then we're taking partial derivatives of all the dimensions of the gradient. Think of the gradient as a function. Yeah? So it's a function that takes in a point in Rd and then outputs also a point in Rd. And the way we computed this function is by computing all the individual partial derivatives and putting into a vector. Of course, now you can do the same thing with the individual entries of the gradient again in order to get the Hessian matrix. Essentially, you're taking the gradient of the gradient function. So if you think of the gradient as a function, you're taking the gradient of the gradient. Let's look at linear regression as an example. In linear regression, we are given some pairs of vectors x, so xi for the ith sample and values yi. So we have continuous values yi. These are element r, and these here are element rd, and we have a total of n of these. So I goes from 1 through n. And what we're looking for is, well, let's, for example, show only a single dimension of x, but here we have our y. And if we plot our data for this one-dimensional special case, we're looking for a line that, if we look at the differences in the y values for a particular point x, so here we have a pair x and y, we're looking for the line that minimizes the sum of the squared differences. So if we compute these differences here between the line and the y value at this particular x, we want to minimize the squared differences. And if we summarize all the x into an n by d matrix x, so it's a matrix that is n times d, and all the y values into an n-dimensional vector. What we want to minimize is our loss, which is the sum of the squares of these differences. Or in vector notation, we can write this as follows. We can write y, the vector of all these y values, minus the vector of all our predictions, which is given by our matrix x times our parameter vector w transpose y minus x w. So w, of course, is also a vector because it has entries as many as we have dimensions in x, of all these weights for the individual dimensions. And summing up these dimensions can be represented by this matrix vector product. So this computes in one go the vector of all our predictions for all our x's. And if we take this vector of predictions and subtract it from our vector of y's, we get basically a vector that contains all these differences here as entries. So sum of squares can be obtained by taking this vector and multiplying it, so building the dot product with itself. And now we can compute the gradient of this function. So let's first simplify it a little bit. We first get y transpose y minus 2y transpose xw plus w transpose xw. Now if you take the gradient of this with respect to the parameters w, then y transpose y doesn't contain w. We are left with minus 2 times y transpose x plus w transpose x transpose x. So in order to get the Hessian, we have to take the gradient of the gradient. So let's just do that. Well, the Hessian is written as this nabla squared WL equals, well, the gradient of the gradient. So let's take the gradient of this term here. So it's a gradient of W of minus 2 y transpose x plus W transpose x transpose x. And what's the result of that? Sorry, there's a 2 missing here. This term here doesn't contain any w anymore, so it becomes 0. And this here does contain w, so what we're left with is 2 times x transpose x. And what is this? Well, x transpose x is a d by d matrix. So the diagonal entries will be the second derivatives, and the off diagonals will tell you how the gradient changes if you change one dimension of your function. Now in principle you're not limited to just computing the Hessian, which is a generalization of the second order derivatives, but you can also go to an arbitrary order k. So the kth derivative of this multivariate function will be a tensor called dkx of f. So it's the kth order tensor of size, well, it's just the gradient was the first order tensor of size d. This Hessian will be a second order tensor, so a matrix of size d by d. So first order tensor is a vector, second order tensor is a matrix, and then we would get three-dimensional tensor. So for the third derivative we would get a third order tensor of size d by d by d, and so on. Now in practice we typically only work for multivariate functions up to the second order derivatives. So if you know how to compute the Hessian, usually you're good. It's very rarely that we would go higher than the Hessian. And of course, we can also use these kth order derivatives, or the generalizations of the kth order derivatives, in order to build a polynomial that approximates our function. So as I said, in practice we never go higher than the Hessian. In this case, this second order approximation would be a parabolic approximation to a function. So we're working with the function value at a point x0, the gradient at this point x0, and the Hessian at the same point x0, in order to build a parabolic function that approximates f. So if f is twice continuously differentiable, then f of any x, which is x equals x0 plus h, can be approximated as a parabolic, that is, where the approximation has the same function value, the same gradient, and the same Hessian at this point x0 by this function f of x0 plus the gradient of f times x0 times h. So if you just use this part, you have your linear approximation. As before, plus now a squared form in the Hessian. So you take your Hessian matrix and you multiply your difference vector h to both sides to this Hessian. So remember, the Hessian is a symmetric matrix of the second order partial derivatives. It's d by d matrix. Your difference vector is a d-dimensional vector. So the result of this will be a scalar times a half. And this will then be a parabolic approximation to the function f that has the same gradient and Hessian. So let's look at a simple example. Well, say we have a function that is in R2, so f goes from R2 to R in this example. Here we have our x1, here we have our x2, and we will visualize this two-dimensional function using level sets. So the third dimension will be visualized here. So these are the two coordinates are the inputs. So our function basically has level sets that form these triangles. And here we would have a maximum, say, and here our level sets would go bigger. No? Now say we pick our x0 here, and we want to do a parabolic approximation. Then we would compute the gradient here. So the gradient would then be a vector that points in this direction. And we would compute our Hessian. And then we would get a parabolic approximation to the function. It has the same Hessian. So the Hessian always gives you the curvature and the same gradient. And it would look something like this. So we get a function that has different level sets. And because it's a parabolic function, it means that the level sets will be ellipses. You already see that it will have a different optimum and will look different. But in this point x0, it will have exactly the same gradient, so vector of steepest increase, and curvature, so the same Hessian matrix. Similar to the Taylor series for univariate functions, we can also generalize the Taylor series for multivariate functions. So for completion, let me introduce to you the Taylor series for multivariate functions, so the multivariate Taylor series. So we have a multivariate function, so a function that goes from R to the D to R. So you take a vector x, and you output, you get f of x, which is a scalar. This function needs to be smooth at this point x0. And in this case, we define our different vector delta as x minus x0. Then the multivariate Taylor series of f at this vector x0 is defined as the sum from k equals 0 to infinity of the kth derivative of this multivariate function, which, remember, is a kth order tensor. So this is not a scalar, but a tensor that is in this fraction here, divided by the kth factorial times the kth power of this difference vector, which again will be a kth order tensor. where this term is the contraction over two tensors. So you have two kth order tensor, and they're of the same size. You're doing a pointwise multiplication of them and summing all the entries together. So what you end up is a sum over all the entries of this tensor. So basically all of these indices here go from 1 through d, and there will be k of these sums, so I1 through ik, the entries of this kth order derivative tensor, times the corresponding entries of this difference vector. So you basically build the outer product over all these difference vectors, which also gives you a kth order tensor, but it's a kth order tensor that is, because it's just outer products of these vectors, will just be a product over the difference vector at the same indices. So the kth order tensor dk is again a matrix or a tensor element R of d times d times d times d. That's k times for this kth order tensor. It is obtained by taking the k-fold outer product of the difference vector with itself. You can denote this outer product using this cross in a circle. So, for example, the squared is the outer product of d with itself, which equals to, well, if d is a column vector with d entries, then you take this d times 1 vector, multiply it with its transpose, which is a 1 by d vector. You get a d by d matrix where the entries are the product of di and dj. So the product of di and dj gives you the ijth entry of this second fold outer product. So let's summarize this lecture on the Taylor series and the Taylor expansion. In particular, important is the second order Taylor expansion. The Hessian is the matrix of second order partial derivatives, so it's the generalization of the second derivative for univariate functions. So if we have a multivariate functions, we cannot just do a second derivative, we get a matrix of all these second order partial derivatives, which is called the Hessian. And we can approximate any function by an affine function, so basically a linear function that is moved somewhere else, away from the origin, using the first order Taylor expansion. And we can approximate any function as by a parabolic if in addition to the gradient, we also have the Hessian matrix, and the result is then basically this parabolic function. So in 2 dimensions, it would be a function where the level sets are ellipses. And with this summary, I would like to say goodbye for the day and see you next time. Bye-bye.